Assalamualaikum and hello everyone. In this section, we will be walking you through the basic of CMOS technology. Today, we will be focusing on three main parts: the 3D structure of CMOS, the layers that make it up, and an overview of how it's actually fabricated. So, let's get started. So, what actually is CMOS? CMOS stands for Complementary Metal Oxide Semiconductor. It is a semiconductor technology used to build integrated circuits, basically the brains inside electronics. What makes CMOS special is that it uses two types of transistors, NMOS and PMOS, and they work together inside the same chip. You will find CMOS being used in microprocessors, memory chips, sensors, pretty much everything we use daily. Some of the main benefits of CMOS are its low power consumption, good noise resistance, and its ability to pack a lot of transistors into a small space. This is why our devices can be powerful while staying small and energy efficient. Now, let's take a closer look at how CMOS is built. CMOS is made up of two types of transistors, PMOS and NMOS. PMOS transistors are created inside an N-well, where NMOS transistors sit directly on the P-type substrate. Both transistors have similar key parts: the source, drain, a thin gate outside layer, and a polysilicon gate on top. The gate controls where the current can flow between the source and drain, which is how CMOS switches on and off. All these parts are connected through metal contact so they can communicate with the rest of the circuit. Next, let's go through the main layers inside CMOS from top to bottom. At the very top, we have the metal layers. These act like wiring to route signals around the chip. Below that, there are contacts or vias, which connect the metal to the layers below. Then comes to the polysilicon layer. This forms the transistor gate. Right underneath is the gate oxide, a super thin insulating layer. Below that are the diffusion regions, where the source and drain terminals are located. These sit inside well region, either N-well for PMOS or P-well for NMOS. And at the bottom of everything is the silicon substrate, which act as the base. So overall, well-defined where transistors are placed. Polysilicon and oxide form the gate that controls switching. Diffusion makes the source and drain, and the metal layers connect everything together to make a working circuit.
Next, let's dive into how CMOS is fabricated.
Step 1. Substrate selection. We begin by selecting a P-type silicon substrate as the foundation of our entire fabrication. This wafer is usually made using the Czochralski process, ensuring high purity and a uniform crystal structure, which is crucial for consistent transistor performance. Step 2. Oxidation. We move to the oxidation stage where a thin layer of silicon dioxide is grown over the wafer surface. This is achieved by exposing the wafer to oxygen and hydrogen gas at around 1000 degrees Celsius in an oxidation furnace. This oxide layer plays two important roles. It serves as a protective barrier and also acts as a masking layer to control where impurities can enter the substrate later. It also provides electrical insulation between different components of the circuit. Now comes the exciting part, photolithography, which defines the layout of our circuit, which is from step 3 to step 5. Step 3. Growing of photoresist. At this stage, to permit the selective etching, the silicon dioxide layer is subjected to the photolithography process. In this process, the wafer is coated with a uniform film of a photosensitive emulsion. Step 4. Masking. This step is the continuation of the photolithography process. In this step, a desired pattern of openness is made using a stencil. This stencil is used as a mask over the photoresist. The substrate is now exposed to UV rays. The photoresist present under the exposed region of the mask gets polymerized. Step 5. Removal of unexposed photoresist. The mask is removed and the unexposed region of the photoresist is dissolved by developing the wafer using a chemical such as trichloroethylene. This process essentially acts like printing to the transistor layout onto the wafer. Step 6. Etching. The wafer is immersed in an etching solution, hydrofluoric acid, to remove the exposed silicon dioxide. This creates windows for diffusion. Step 7. Photoresist removal. The remaining photoresist layer is stripped off using hot sulfuric acid. Step 8. Formation of N-well. N-type impurities such as phosphorus or arsenic are diffused into the P-type substrate through the exposed regions to form the N-well, which later holds the PMOS transistors. Step 9. Oxide removal. The silicon dioxide layer is removed completely using hydrofluoric acid, preparing the surface for gate formation. Interesting fact, the diffusion temperature and time must be carefully controlled. Even a few seconds difference can alter the transistor's performance. Now that the wells are formed, we move to building the gate structure, which controls the flow of current in the transistor. Step 10. Deposition of polysilicon. The misalignment of the gate of a CMOS transistor would lead to the unwanted capacitance which could harm the circuit. So to prevent this, self-aligned gate process is preferred where gate regions are formed before the formation of source and drain using ion implantation. Polysilicon is used for formation of the gate because it can withstand the high temperature greater than 80,000 degrees Celsius when a wafer is subjected to annealing methods for formation of source and drain. Polysilicon is deposited by using chemical deposition process over a thin layer of gate oxide. This thin gate oxide under the polysilicon layer prevents further doping under the gate region. Step 11. Gate patterning. Unwanted polysilicon is etched away, leaving only the gate structures for NMOS and PMOS. Step 12. Oxidation process. An oxidation layer is deposited over the wafer, which acts as a shield for further diffusion and metallization process. By this stage, both the NMOS and PMOS gate regions are neatly defined and insulated. Step 13. Masking for N-type diffusion. In this step, we begin preparing the wafer for N-type diffusion. A new photoresist layer is applied and patterned to open small gaps near the NMOS gate area. This selective exposure allows us to define the exact location where the source and drain terminals of the NMOS transistors will be created. Precise masking here is extremely important, as any misalignment can cause unwanted overlap or short circuits later on. Step 14. N-type diffusion. Now, we perform the N-type diffusion process. Using the openings created by the mask, N-type impurities such as arsenic or phosphorus are diffused or implanted into the exposed regions beside the NMOS gate. This forms the source and drain regions for the NMOS transistor. After diffusion, the wafer is annealed at a high temperature to activate the dopants and repair crystal damage caused by ion implantation. Step 15. Oxide removal. The protective oxide is stripped away to prepare for PMOS formation. Step 16. P-type diffusion. Similarly to P-type, impurities such as boron are diffused into the N-well to create source and drain regions for the PMOS transistor. Additional fact, ion implantation has replaced simple diffusion in modern CMOS because it allows better control of doping concentration and junction depth. Step 17. Field oxide formation. Before forming the metal terminals, a thick field oxide is laid out to form a protective layer for the regions of the wafer. This helps to isolate and protect the transistors from unwanted electrical interactions.
Step 18. Metallization. In this step, a thin layer of aluminium is deposited across the entire wafer surface. This aluminium layer acts as the wiring system of the chip, connecting different transistor and circuit components together. It forms the crucial interconnections that allow signals and power to flow throughout the integrated circuit. Next is step 19, metal etching. Here the unwanted aluminium is removed through a controlled etching process. Using photolithography, only the desired metal path remain that form intricate interconnections between transistor terminals. Step 20, terminal formation. At this stage, small openings are created to expose the contact regions, such as the source, drain and gate terminals. These openings allow the circuit to connect to external pads or wires later. Finally, step 21, terminal naming and finishing. Each transistor terminal is identified and labeled as S source, G gate, D drain and B bulk. This marks the completion of the CMOS fabrication process, where both NMOS and PMOS transistors are now fully formed and interconnected. With every layer formed and terminals defined, here's how the completed CMOS device looks in cross-section. So, to sum it up, CMOS fabrication is an intricate process that transforms a plain silicon wafer into a network of millions or even billions of transistors. Every step, from oxidation to diffusion to metallization, must be executed with nanometer precision to ensure proper functionality. The end result is a compact, low power and high-speed integrated circuit that forms the backbone of all modern electronics. But wait, before we end, you can actually see one transistor up close. Just scan this QR code to view the model in augmented reality. Watch the layers and structure appear right in front of you. Thanks for watching.